Well, let's start the lecture 6.2. Today we're going to continue our discussions about the continuous random variables. In particular, we're going to talk about the exponential distribution and uniform distribution. So it is really important for us to start with the exponential distribution, even though in the textbook it comes at the end. It is a little bit more difficult distribution to understand, but I think we can do a small introduction to the exponential distribution and try to connect this with the other distributions which we have discussed in the previous week. We also are going to discuss how to calculate the expected value and the variance in the continuous case. So let me start with the introduction of how we are defining the continuous random variables. If you remember, in a discrete case, we are given the mass function, where the mass function are going to be simply the points. And if I would like to evaluate the probability, I will just go to those points and get the heights, right? And that's going to be the probability. Well, in this case, the x-axis is going to be the output, and the y-axis is going to be right immediately the probabilities in the discrete case. So for the continuous case, it is difficult to do this because the continuous variables are going to take infinitely many points, and it is not like easy for us to define this just using the points. So we are going to define them using the function, which we are going to call as the density function. So please know that the density function is not going to give you the probability right immediately. So for example, if I just go to here, if I would like to find what is the probability if the x is equal to 10, I can't just really go to here and get the value of this function because this is not going to be the probability anymore. So I think in this case, I would just change the notation for the p of x. It should be f of x probably. It's not the probability anymore. For example, let's assume that x now is the random variable which basically measures the time you wait for the next train when you come to the university. So you might wait like 0 minutes or like 5 minutes or 10 minutes or anything in between. And if you would like to value the probability of waiting time between 5 and 10, what you're going to do is you are going to take the area under this curve. Okay? So this area here, which we can find using the integration, is going to be the probability. Again, the curve is not the probability anymore. The area under the curve is the probability. So in the sense, we need to know how to make the integrations for many functions. And also, we discussed about the properties of the density function, and one of the main properties of the density function is that the total area under the curve should be equal to 1, right? As what we did before for the probability. So the total probability is equal to 1, and we are distributing this through the different outputs, okay? And also, it is important to mention that when we are going to evaluate the probability of a random variable, the continuous random variable, at the single point, it is going to be equal to 0. If I say, what is the probability that you're going to wait exactly 5 minutes? The train, I would just say 0, okay? It doesn't matter what is the curve, what is the density function. The probability of a random variable at the single point is going to be 0. Okay, so let's start with the case, with an example, when I would like to simulate these different situations in a bank. So let's assume that you go to the bank and you have to wait for your order and the cashier. And in average, let's say, one cashier, like a cashier number 11, let's say, she serves 6 clients every hour, in average. Okay? So if I know this, can I find the probability that next hour she's going to serve again 6 clients? So when I say that she serves 6 clients in average, it means that people, what they did is she counted how many clients she has been serving for many hours. Like for the first hour, she has been serving like 7, then 6, then 5, right? Then in average, she's got this number 6. So I would like to evaluate the probability that in the next hour, she's going to serve again 6 clients. So how we can find this probability? Or what is the number of the, so is it the number of the clients which she's going to serve in our random variable or not? It's random, right? So you can imagine the situation in a bank. So you go to the bank and you can imagine that the clients who are coming to the cashiers, right, the number is the random variable, okay? And what we need to do is we need to evaluate the probability that this random variable is equal to exactly to the 6. Is it a discrete random variable or the continuous random variable? The number of the clients. discrete, right? Okay, so which distribution we need to use in order to evaluate this probability? Poisson, right? So do you remember the Poisson distribution is going to give you the probabilities of the occurrences, of the number of the occurrences of the event, right? In some period of time. And if you are given that in 1 hour, she serves 6 clients, right? So in average, we are going to use this as the parameter of the Poisson distribution. So the lambda is equal to the 6, and then we just need to put this into the formula of the Poisson distribution. So the k is equal to the 6, and if you remember, the probability of x is equal to the 6 is going to be e in the power of minus lambda, which is 6, times the lambda 6 in the power of k, which is 6, divided to the 6 factorials. It's going to be 0.16, 16% that next hour there will be 6 clients who are coming. Okay? So, well, let's assume that you went to the bank. I mean, whenever I go to the bank, I actually don't care how many people there are, whether there are many people or like not many people. What I care is how much time I have to wait. I don't care how many people there, right? So it is important for me to know whether I'm going to wait less than 5 minutes or more than 5 minutes or like more than 10 minutes and so on. So let's try to simulate that case. So let's assume now that the first person who came went into the bank and she's now going to wait for her order. So while the first client is going to be served. Okay? So what I want to know is, I would like to know how much time she's going to wait for her order. So it appears the time she's going to wait is the random variable, right? So she may wait like for 1 minute, or she may wait for 10 minutes, or she may wait for 20 minutes. It's a random variable. And it is, in this case, a continuous random variable. So the number of the people who are coming to the bank is the discrete random variable because we count this. And the amount of the time while the client is waiting for her order is the continuous random variable. Okay? And it is also, and it has the density function, which is given by this function. Okay? So this is kind of difficult function. We're going to use this function now in order to evaluate the probabilities. Okay? So let's assume that the waiting time for the second client is the random variable, and its density function is given like this. Okay? Where lambda is going to be some parameter, we first of all have to find what is the lambda, then we are going to evaluate the probabilities. Okay? So if the waiting time has the following density function, what is the value of the lambda so that it is going to be the proper density function? What is going to be the probability that the waiting time is less than 5 minutes? And what is going to be the probability that the waiting time is between 5 and 15 minutes? Okay? So do you remember how we can find the lambda? So if, for example, the lambda is equal to the 0, is it going to be the density function? So if you substitute lambda to be equal to the 0 here, then the density function is going to be all the way zeros, right? Which is not a density function because we know that the total area under the function should be equal to the 1, right? So if I choose the lambda to be equal to the 1.5 or 1 or 2.5, is it going to be the proper density function or not? Well, we can check this, right? So how we can choose the lambda? So we need to choose the lambda in a way that the total area under the density function should be equal to the 1. Okay? Cool. So let's find the integration. So the integration of this function from 0 to the infinity. So of the f of x, which is lambda times e in the power of minus x divided to the 10 dx. Okay? So since lambda is a constant, I can take this out from the brackets. It is going to be the lambda times integration from 0 to the infinity e in the power of minus x over 10 dx. Well, can you tell me what is the antiderivative of the e in the power of minus x over 10? It's going to be minus 10 times the e in the power of minus x divided to the 10. Can you explain why? So why the antiderivative of the x in the power of minus x over 10 is equal to the minus 10 times the e in the power of minus x over 10? Well, let me explain. So for example, what is the antiderivative of the x? X squared over 2. Why? Because if you take the derivative from the x squared over 2, you're going to get x, right? The same is here. So the antiderivative of the e in the power of minus x over 10 is equal to the minus 10 e in the power of minus x over 10 Because if you take its derivative, it's going to be e in the power of minus x over 10. Okay? So now we're going to continue our calculations. I'm going to substitute the infinity. It's going to be lambda minus 10 times the e in the power of minus infinity plus 10 lambda e in the power of minus 0 over 10. So I've substituted x was the infinity and the 0. So please note that this term is going to be equal to the 0, right? Because when the power of the e goes to the minus infinity, it's going to be 0, right? So it is basically you're dividing 1 into the huge number. And the second term is going to be equal to simply 10 lambda, because e to the power of 0 is 1. And all of these terms should be equal to the 1. And from here, it is clear that lambda should be equal to 1 over 10. Okay? So if the density function is given like this, where the lambda is some constant, then lambda should be equal to the 1 over 10. Only in this case, it is going to be the proper density function. Not when lambda is equal to the 0 or 1 or 1 over 2. It is exactly just in this value, 1 over 10. So now we can just substitute the lambda to be equal to 1 over 10 and evaluate the probability. So what is the probability that the client is going to wait for less than 5 minutes? So again, now you are given the density function, you can evaluate any probabilities, right? So you can imagine that the density function is some curve. So in this case, it's going to be the exponential function, okay? And if you need to find the probability, you just need to integrate this. So the probability that a client is going to wait for less than 5 minutes is going to be the integration of the density function from 0 to the 5. So actually, you have to integrate from minus infinity to the 5. But since our function is simply 0 in all of the region from minus infinity to the 0, I don't need this term. I'm going to substitute this from 0 to the 5, 1 over 10, e in the power of minus 5 over, x over 10, sorry. X over 10 dx. And I'm going to take its antiderivative again. So the antiderivative of this term is going to be minus e in the power of minus x over 10. Right? Because if you take the derivative from this, from minus e to the power of minus x over 10, you're going to get exactly this term. Right? So we have to substitute 0 and 5. So we have to substitute 0 and 5. And if you substitute the 5, it's going to be minus e to the power of minus 1 over 2. If you substitute the 0, it's going to be simply 1. Well, can you now evaluate this? So basically, you have to take the square root of the e and find its reciprocal and subtract this from the 1. What is this value? Okay, 0.39. Okay, probability that she's going to wait less than 5 minutes is 39%. So let's do one more exercise. So what is the probability that she's going to wait between 5 and 15 minutes? So in this case, what you need to do is you have to find the probability that she's going to wait between 5 and 15 minutes. It's going to be the integration of the density function between 5 and 15 dx. And we know what is the antiderivative already. It's going to be minus e in the power of minus x over 10, right? And we have to substitute the 5 and 15. It's going to be minus e in the power of minus 3 over 2 plus e in the power of 1 over 2. Where's the minus? Okay, can you evaluate this now? It is basically 1 over square root of e minus 1 divided to the e cubed from the square root, right? Yeah. Okay, 0.38. Okay, the probability that she's going to wait between 5 and 15 minutes is equal to the 38%. Okay, is it clear how to make the calculations? So if you're given the density function, it is super easy to make the calculations, okay? Not easy, but straightforward. You just integrate this. And if you don't know how to integrate this, you can always integrate this numerically or approximate the integration. The question is, why exactly we have to use this function? And if we are using this function, why this 10 or from where this 10 is coming from? Is it like this 10 is some special number, or it doesn't matter which number we're going to use? What do you think? It matters, right? So do you remember I told you, hey, there are 6 clients have been served in this bank in average, in 1 hour, right? In 1 hour, in average, there are 6 clients have been served, right? Then we're using the density function for the waiting time, and we're using 10. or 1 over 10. What do you think? Are these two problems are connected? Or is it possible to know this 10 from the previous problem? If there are 6 clients are being served in 1 hour, in average, right? Then in average, every client is waiting 10 minutes. Okay? So this 10 here is actually average waiting time. Okay? So in a Poisson distribution, we are evaluating the probability of the number of the clients that have been served, and we have to use the average number of the clients. And in this probability distribution, we are using this function, and here the parameter is going to be the average waiting time. Okay? So in general, we can use this kind of distribution for any random variable which denotes the waiting time, and the distribution of the waiting time is going to be called as an exponential distribution, and its density function in general is going to be given like this. Okay, so the distribution of the waiting time is called the exponential distribution, and you can simulate many different situations using the waiting time. For example, you can find the probability of waiting time of the bus, or you can estimate the probability of the waiting time of your professor in the lecture when he's late, right? Or you can evaluate the probability of waiting time of your food in the canteen. Or you can do this even with the with for example the battery replacement of your phones. For example, if you know the average lifetime of the battery of your phone, you can evaluate the probability of how much time your battery on your phone is going to work. For example, if I say, hey, I've got a phone whose battery is alive for 100 hours or 100,000 hours. No, it's a lot. 100 hours, let's say, okay, in average. So it means that some phones, so for example, the iPhone manufacturer is going to claim that, hey, the batteries of this phone works for 100 hours. Okay, how do they know? So they produce the new phone and they are saying, hey, it works for the average 100 hours. So what they did is they took a sample of like 100 phones, for example. They use their phones a lot and they can estimate the average lifetime of their batteries. Okay? And now I just can buy a phone and I can estimate the probability that this phone is going to work more than 100 hours using this function. Okay? So do you feel the connection, relationship between the Poisson distribution and exponential distribution? So the Poisson distribution is the number of the events occurring in some period of time, and the exponential distribution is the time between every occurrence of those events. Okay? And these lambdas in the Poisson and the exponential are obviously different things. And the Poisson lambda is the average number of the events occurring in some period, and here this lambda means the average waiting time, okay, or reciprocal of the average waiting time, by the way, because if you remember it was 1 over 10, right? So we call this as the rate. So the lambda is the reciprocal of the average waiting time. Okay, so it is called as rate. Like, do you know what's the frequency, for example? If you've got some clock which rotates like 10 times in 1 second, right? Then its frequency is going to be 1 over 10 hertz. Okay, this is the same. Like if there are like 10 minutes, it's an average waiting time, then the lambda is going to be 1 over 10. Okay, so if I say that another cashier in that bank serves 3 clients in every hour, then what lambda I have to use? If the cashier number 12, another cashier, serves 3 clients in every hour, in average, what is going to be the lambda here for the exponential distribution? 1 over 20. Okay, so the 20 is the average waiting time, because in 1 hour there are 3 clients. 60 minutes divided to the 3 is 20 hours. In average, every client should wait 20 minutes, right? The lambda is going to be 1 over 20. So the exponential distribution is very important, and we're going to use the exponential distribution a lot. And we are going to discuss about the exponential distribution a little bit more in details after a couple of lectures. But I've decided to discuss with an exponential distribution today because it is very much connected with the Poisson distribution, and it is very much easy for me to give you the quiz on this, both of the topics. Okay? So then we are going to come back to the exponential distribution again. So the first and one of the easiest distributions, continuous distributions, is called the uniform distribution. But if you remember, we used to have the uniform distribution in the discrete case as well. Right? What does it mean that random variable has a uniform distribution? Well, for example, let's say you roll a die and the random variable x is going to be the output of your experiment. So do you remember what are the probabilities of getting 1 or 2 or 3 or 4, 5, 6? 1 over 6 always, right? So the probability mass function for this random variable is going to look like this, right? For all of the outputs of the x, it is always going to be 1 over 6, okay? So since the total amount of the probability is 100%, it is distributed through all of the outputs of your random variable equally, okay? So this is what does it mean, the uniform distribution. The distribution of random variable is how this 100% is distributed, is split over the different outputs of the random variable, right? And the uniform distribution means that this 100% of the probability is distributed, is split over all of the outputs equally. If you would have, for example, 4 outputs, then the probability, and if I say, hey, the x is going to have the uniform distribution, then every output is going to have the probability of 0.25. Okay, because 1 is distributed, is split into the 4 equally. This is what does it mean, the uniform distribution. So what do you say? If your random variable x is given, or is said that has the uniform distribution, what is going to be the density function of this random variable? So let's assume that x has a uniform distribution in some interval. What is going to be the density function of this x? Well, it's going to be simply the horizontal line. Okay? So let's say, so we are given some interval. A, let's say it's going to be 4, okay? Or let me write as A. So I hope that you understand what does it mean. So the B is going to be here. Your random variable can be any number between A and B. Okay? If A is, for example, 4 and B is equal to A, your random variable can be any number between 4 and 8. And the chances to occur to any number are the same for all of the numbers. Okay? So if I would like to draw the density function here is going to be something like the horizontal line. The only question is, so what do you think if I just spread this interval, A and B, or if I just squeeze this, make them like more closer to each other? What do you think? Is it like the height of this horizontal line is going to change or not? No, it's not going to be the same. It's going to be always the same. If I, for example, squeeze this, it is going to be like the line is also going to be squeezed?
No. Change.
Yes or no? Is it going to change the height of this line? Of course, yes, right? If you're going to just make this A and B wider, then this line should go lower, okay? And if this A and B are going to go closer to each other, then this line goes upper. The reason why it is going to happen is that the total area under this line should be equal to 1, right? Obviously, you've got a rectangle, right? The area of this rectangle is always equal to the 1. If you just increase the width, then obviously the height should decrease because the area is 1. Or if you decrease the width, then the height is going to increase, okay? So what is going to be the height here, by the way? What is the height? At which point? What is the point here on the y-axis? 1 over b minus a, right? The reason is the area under this curve, which is going to be exactly the rectangle, is equal to the width times the height. So the width is b minus a. So the height should be equal to the 1 divided to the b minus a, so that it is going to be equal to the 1, right? So we choose the height of the curve when your random variable is given as the uniform distribution as the reciprocal of the width of your interval, okay? Because the area should be equal to 1. Okay, so let's write this down in general case, and we're going to do a couple of exercises on this. So let x is given as the uniform distribution in some interval, then its density function is going to be equal to the 1 divided to the b minus a if x is from this interval and 0 otherwise, and its cumulative distribution function is going to be slightly different. So I think we need to talk about the cumulative distribution function in a moment. So let's talk about the cumulative distribution function. So now it is clear that the height of this line between a and b should be equal to the 1 divided to the b minus a, right? Okay. So do you remember what was the cumulative distribution function? The cumulative distribution function, f of x, let's say. It is the probability that your random variable is smaller or equal to the x. Okay? So again, if you remember, there is a difference between the capital X and the lowercase x. The capital X means your random variable. The small x is a specific value. Okay? So now, if I know what is the density function of the uniform distribution, can I find a cumulative distribution? So what is the probability if x is any number before the a? For example, a is equal to the 4. What is the cumulative distribution of any number before the 4? So for example, if I say, what is the f of 4? Or f of, so if a is equal to the 4, what is the cumulative distribution of the 3? It is the probability that your random variable is smaller or equal to the 3, or it's the integration of the density function from minus infinity to the 3. It's all the way area from minus infinity until the specific point. This is what does it mean, the cumulative distribution, right? So when you substitute the cumulative distribution with some x, it is the all the way area from minus infinity until this x, right? So what is this probability? When x is chosen to be equal to some number which is smaller than a. What is the area? So since this curve is 0 always until the end, it is going to be 0. Okay? This is 0. If x is smaller than a. What if x is in between a and b? For example, if x is here, what is going to be the cumulative distribution here? 1? No, it's not going to be 1. It's the area from minus infinity until the x, right? It is going to be this area. So all of this area, which is 0, plus this area. What is the area of this region? X minus a divided to the b minus a. And if x is here in some area bigger than, in some point, after the b, then the area is going to be all of this area plus the rectangle plus the area here, which is always going to be equal to the 1. Okay? So this is going to be the cumulative distribution function of the random variable, which has the uniform distribution. So if x has the uniform distribution in between a and b, then it's going to have the density function like this, and the cumulative distribution function is going to be like this. So it's going to be simply 0 if x is smaller than a. It's going to be x minus a divided to the b minus a if x is between a and b. And it's going to be equal to the 1 if x is bigger than b. Let's do an example. So let's say that buses arrive to the specific bus station or the train station every 50 minutes, starting from 7. So at 7, at 7:15, 7:30, 7:45, and so on. So let's assume it's not a bus station, it's a train station, okay? So that they always arrive at the specific time, okay? So let's assume now that Vadim came to the, so he always takes this train, okay? And the time when he arrives to the station is random. He can arrive at any time between 7 and 7:30 to the station. Okay, any time. And the time when he arrives to the station has the uniform distribution between 7 and 7:30. So the chances that he can arrive to the station at 7 is the same as the chances he will arrive at 7:05 or 0:15 or 0:25. Okay? All of the chances are the same. So now what I would like to know is, if I know that he comes to the train station at any time, at random time between 7 and 7:30, what is the probability that he's going to wait for the next bus less than 5 minutes? Okay? It is slightly different than what we've discussed before. Okay? Previously, it was the waiting time, right? We did this. But actually, this distribution is not about the waiting time. It's about when he arrives to the station. Okay? Do you understand this? Yes. So, even though I'm asking you the question to find the probability of the waiting time here, it is not a problem about evaluating the probabilities of the waiting time. It's a problem of evaluating the probabilities when Vadim came to the station. Okay, so that is why we don't use the exponential distribution. Okay, so when he waits less than 5 minutes, when he should arrive to the station so that he's going to wait less than 5 minutes. So he should arrive to the station between 7:10 and 7:15 or 7:25 and 7:30, right? Again, so I'm asking this question differently. So I'm asking you actually, what is the probability that he's going to arrive between 7:10 and 15 or 25 and 30? And I've rephrased this differently. What is the waiting time? What is the probability of waiting time is less than 5 minutes, right? So let us do this. So the probability that waiting time is less than 5 minutes. It is the same as finding the probability that he's going to arrive between 10 and 15 or 25 and 30. Okay? So since the random variable x has the uniform distribution, we have to first of all derive its density function, and then we are going to integrate this in the given intervals in order to find the probabilities. So what is the density function of this random variable x? The density function here is equal to the 1 divided to the, what is the length of the interval? 30, right? It's going to be 1 over 30 if x is between 0 and 30, and it's 0 otherwise. Okay? Again, x is the time when Vadim came to the station, and it is a random variable which has the uniform distribution between 0 and 30. So that is why its density function is going to be 1 divided to the length of the interval, which is 30 minutes. Okay? So I just need to integrate this. So if I would like to evaluate the probability that he is going to arrive between 10 and 15, it is going to be the integration between 10 and 15 of this density function, which is 1 over 30 dx. Do you remember what is the antiderivative of the 1 over 30? It's simply x over 30, right? And we have to substitute the 10 and 15. If you substitute the 15 and 10 and subtract, it's going to be 5 over 30, which is 1 over 6, right? So please note that the probability that he's going to wait between 25 and 30 is the same, right? So if you just add these two probabilities, the answer is going to be equal to the 1 over 3, okay? The probability that he's going to wait less than 5 minutes is equal to the 1 over 3. But again, so this is completely different than what we did before. Okay? Before we actually evaluated the probability of waiting time. Here, even though I'm asking you to evaluate the probability of the waiting time, you are calculating the probability of the arriving time. This is the uniform distribution. So there are a couple of distributions we're going to discuss in this semester about the continuous random variable. So one is the uniform distribution, another the exponential, and the third one is the normal distribution, which is one of the most important distributions which we're going to learn. And we're going to discuss this next week. But this week we're going to rather talk about the properties of the continuous random variables, such as like exponential, expected value, and the variance. Okay? So let's discuss how we can calculate the expected value and the variance for the random variables in the continuous case. So we are going to define the expected value for the continuous case in a very much similar way as we did for the discrete case. If you remember, in the discrete case, in order to evaluate the expected value, we multiply the x to the probability. Do you remember this? So the x multiplied to the probability of mass function. Then we did the summation, right? So when it goes into the continuous case, it becomes the very much definition. Okay? We're going to multiply the x to its density function, and then we're going to integrate this. Okay? It's going to give you the average value of the x. Oh, by the way, if you would just integrate the density function, what does it give it to you? Do you remember how to find the average value of the function, of any function? For example, if you're given some parabola like this, okay? If you would like to find the average value of this function, like f of x, the average value of this function, of f of x is going to be the integration of the f of x between, for example, 0 and a, between 0 and a dx times the reciprocal of the width of this interval. If you remember, we discussed this in the calculus, how to find the average value of the functions. Okay? Please note that expected value is not the average value of the function. So we are evaluating the average value of the x. What is the x? The random variable is in average, not the density function, not the function. Okay? Cool. So we're going to evaluate the expected value using this formula, and we're going to do a couple of exercises. So if x has the uniform distribution between 0 and 1, what is the expected value of the x? The expected value of any random variable is going to be the integration of the x times the f of x. So since x is given as uniform distribution between 0 and 1, I can easily find its density function. The density function is going to be equal to what? It's 1 if x is between 0 and 1, and it's 0 otherwise. Right? Because we are given the interval between 0 and 1, and the width of this interval is 1. The reciprocal of the width is also equal to the 1. So I'm just going to substitute this to the formula. So the expected value of the x is going to be the integration of x times to the 1 dx from 0 to the 1. The antiderivative of the x is x squared over 2. We have to substitute the 0 and 1. It's going to be 1 over 2. Okay? And it's kind of clear that if x has the uniform distribution between 0 and 1, then average, its value is equal to the 1 over 2. Let's do a couple of more exercises. It's kind of a little bit difficult. So let's evaluate the expected value of the e in the power of x if x is the random variable. So if you remember, we've discussed the expected value of some function in a discrete case. So for example, do you remember how to evaluate the expected value of the x in a square in a discrete case? It was simply the x squared times the p of x. It was like a famous example when we simulated when we played a game, when someone is going to roll a die and guess the square of the result, right? So this is how we evaluated this in the discrete case. In the continuous case, we're going to do pretty much the same operations. The expected value of some function of a random variable is going to be the integration of this function times the density function of the x in this interval from a to the b. Okay? And we are going to do the similar calculations in order to evaluate the expected value of the e in the power of x. It is going to be the integration from 0 to the 1 e in the power of x times the what? To 1, right? Because the density function of the x is equal to the 1 in this interval. It's going to be multiplied to the 1 dx. The antiderivative of the e in the power of x is also e in the power of x. Okay? We have to integrate this from 0 to the 1, and this is going to be equal to the e minus 1. Well, it is how we can find the expected value of the e in the power of x very easily. Well, we can do this a little bit more difficult. We can evaluate the expected value of the e in the power of x by finding its density function. Okay, we are going to discuss this later on. Okay, so next lecture, we're going to discuss how we can evaluate the expected value of the e in the power of x by just integrating x times to the distribution of that interval from a to the b dx, where f of x is going to be the density function of e in the power of x. Okay, so by the definition, you can evaluate the expected value by just multiplying x to its density function, right? So here we use the different formula in order to evaluate the expected value of the e in the power of x, but it is possible to do this differently by just finding the density function of the new random variable and then multiplying this to the x and integrating this. So in our next lecture, we're going to discuss how we can derive the density functions of the new variables which are associated with our given random variable. Okay? So today we are going to discuss about the variance. So do you remember how we calculated the variance in a discrete case? So it was the average distance between all of the points and the mean, which is defined pretty much in the same way in the continuous case as well. We find the distance between all of the points and the mean in the square and take its average, take its expected value. And if you expand this, you're going to get this formula. So e of x in the square minus e of x. Can you find a mistake here, the typo in this formula? Square here, right? E of x square minus e of x in the square. So let's do a small exercise. So let's say the density function of a random variable is given like this. So I would like to find the variance of the random variable x. So in order to do this, we need to evaluate the expected value of the two random variables, of the x and of the x in the square. The expected value of the x is going to be integration of the x times the density function. What is the density function? 2x. And we have to integrate this from 0 to the 1. Okay, so should I write the expected value of the x is equal to the integration of the x times the density function, okay, between a and b. And if you multiply this, it's going to be 2x in the square. What is the antiderivative of the 2x in the square? 2x cubed over 3. And we have to substitute the 0 and 1. If you substitute the 1, it's going to be 2 over 3 only. If you substitute the 0, it's going to be 0. So the expected value of the x in the square is going to be between 0 and 1, x squared times the 2x dx. So if you multiply, it's going to be 2x in the power of 3. What is the antiderivative of this? 2x in the power of 4 divided to the 4. Again, we have to substitute the 0 and 1. It's going to be 2 over 4 or 1 over 2. And the variance of this variable x is going to be the expected value of the x squared minus the expected value of the x in the square is going to be equal to the 1 over 2 minus 4 over 9. If you give the common denominator, it's going to be 9 minus 8, right? Divided to the 18, or it's going to be 1 over 18. Okay? So this is how we are going to evaluate the variance of a random variable in a continuous case. And this is pretty much in the same way as we did this before. Okay? Cool. So today we discussed about the exponential distribution and the uniform distribution. We've learned how to evaluate the probabilities in a continuous case, and also we've learned about how to find the expected value and the variance of the random variable. So in our next lectures, we're going to discover more about the continuous random variables. Thank you very much. Have a nice holidays. Bye.